in Pharmaceuticals in association with Higher Secondary Principals Forum.
A very good morning, students, and welcome to the second session of Ray Optics chapter. I, Mrs. Bhakti Bandekar from Santa-Cruz Higher Secondary, Santa-Cruz. I'm sure you have all understood whatever we had done last time. I'll just revise a bit. For the last session, we learned about the reflection of light, about the mirrors, the mirror formula, refraction at plane surfaces, correct? And in total internal reflection and some applications of it. So something really interesting topics we had learned. So let us go ahead with it, and today we'll be dealing with the refraction at curved surfaces. So you can have a look at it. You have got a picture and you can see the inverted image, correct? Yes, of an object. So we are going to learn about the curved surfaces. We'll be learning about the lenses, the lens maker's formula, and few optical instruments. Now as we know, a lens has got two curved surfaces. Okay, it's going to be like this. So first let us check out for the lens. So here I have got a convex lens, and you know it has got this curved surface and this one. So which means it is bounded by two of them. And this is the focus of the convex lens. You can check out, we have got the rays which are coming parallel. After refraction, they are getting converged at one point, and this particular point is the focus. So convex lens is the converging lens. It focuses the rays at one particular point. Just like in mirrors, we have certain terms which we need to know. There's a principal axis, the center will be termed as the optical center. So that was for the convex lens. Now here I have got a concave lens. As it is clear from the picture, this is the parallel rays of light parallel to the principal axis. After refraction, they are moving outward, isn't it? They are diverged. The concave lens is known as a diverging lens. So we need to produce them backward to get the focus. So here is how the focus, concave lens focus we have got. Let us go ahead. Now we have got a small derivation for the refraction at a spherical surface. So here you have got the ray diagram. Okay. Now listen carefully to me, students, because this derivation then again advances. We will be learning about the lens maker's formula, which will be using the final expression for this one. Okay. So let me first explain you the ray diagram. Can you see we have got a curved surface, isn't it? So that's a curved surface separating the two media. It has been given as N1, the refractive index of this medium, and the next is the N2, the refractive index of the second medium. I can say it's a denser medium and the rarer medium. So we have got the point object O, the ray of light is heating the refracting surface and getting refracted, and the final image we get is at I. Okay. So this is the path of the ray of light. We have the point object and we get the point image. In order to get the angle of incidence and the angle of refraction, we have drawn the normal. So can you see here the dotted lines? So these dotted line is the normal at the center of curvature. So if we know this is center, we know this is the radius of curvature, and hence we get here angle of incidence and angle of refraction. U is the distance of the object from the center, and V is the distance of the image. Now, so let's begin with the derivation. So it's a very simple ray diagram. We first take the 3 base angle, the tan of the 3 base angle, that is angle NOM, that is this angle, angle NOM, angle NCM, this one, NNIM. Okay. And we know the tan of each of them. So, the first, that is NOM, will be definitely NM upon OM, which is written over here. NCM is going to be NM upon MC, and NIM, that's MN upon MI. So, when we start off, we just take the tan of the three angles. Now, for the triangle NOC, that is this particular triangle NOC, you can see I is an exterior angle. This I becomes an exterior angle, and we know with our previous knowledge that this angle is the sum of NOM and NCM, correct? And we have already got what is NOM and NCM from the previous. So, just substitute, you will get the equation number 1. So, here I have got the angle of incidence. Now, let us get angle of refraction. Now, concentrate on this triangle NIC. For NIC, this angle becomes an exterior angle, that is NCM becomes an exterior angle, which will be the sum of this R plus NIM. So, you just need to do a slight mathematical steps, and ultimately R, that is the angle of refraction, you get it as Mn upon MC minus Mn upon Mi. So, I have got here angle I have got here angle R. So, let us substitute them in the Snell's law. So, let us use the Snell's law. We all know this, that is N1 sin of I equals to N2 sin of R. So, substituting I and R and cancelling out, this is what we get, N1 OM plus N2 MI, N2 minus N1 upon MC. Now, what is OM? OM was the object distance, MI was the image distance, and MC was the radius of curvature. Let us check out the figure. So, here check out the figure, students. As I have told you, OM is the object distance, MI is the image distance, and MC is the radius of curvature. As per the sign convention, we have given the signs. We have learned it in the first part how to assign the signs. So, let us go ahead. So, as per the signs, we get this OM equals to minus U, MI is plus V, and MC is plus R. So, substituting, the equation becomes this N2, that is the second refractive index upon the image distance minus the first refractive index upon the object distance equals to N2 minus N1 upon R. So, this is what you need to remember, students. Okay, so, this is the final equation that we get. So, this is for the refraction at the curved surfaces, and I will be using this in order to derive the lens maker's formula. So, this is an important equation. Okay, students, so let us solve one simplest problem. So, here it is said that locate the image of the point object O in the situation shown in the figure. So, figure is given, we have got the object O, it is at the 15 centimeters, the Ri is given as 1, the refractive index of this medium is given as 1.5, radius of curvature is given as 30 centimeter. So, please write down whatever is given. So, as per the sign convention, we know this is minus 15 and this is plus 30. So, we have got the formula. What you need to do is substitute and get the answer. So, check out, that will be your answer. Now, let us go ahead, students. Now, we will be starting with a very important derivation. We will be learning about the lens maker's formula and then the thin lens formula, something really very important. So, here refraction by a lens. Look carefully at the figure, the ray diagram. We have got the lens, the principal axis. Here we have got the object, the point object, and forming the image at I, U object distance, V the image distance. And this is the path of the ray of light. Now, as I have told you, lens is a formation of the two curved refracting surfaces, isn't it? It has got 1 and 1, that is two curved refracting surfaces. So, this particular image formation is seen in two steps, that is first refraction through the refracting surface ABC and the refraction to the refracting surface ADC. So, let us see how is it. Very simple ray diagram, students, so just concentrate over here. So, we have the object O, the ray is incident at the curved refracting surface, the ray is getting refracted and forming an image at I1. There is a separation of the two media, hence we have got N1 as the refractive index and N2 as the refractive index of this one. Now, as I have told you, is a curved surface, isn't it? So, you can think of a sphere over here. If this is thought as a sphere, we know the center is going to lie inside. So, if this is your center, this is going to be a radius. Okay, so it is marked as C1 and R1. Fine. So, this is at ABC. Let us go for the next part, that is ADC. Now, for the surface ADC, the I1, the image which was formed over here I1, is acting as the virtual object and the final image is formed at I. So, over here again there is a separation of the two media, so it is marked as N1, over here is marked as N2. Now, this is a sphere as I have spoken about. So, definitely if this is a sphere, the center will lie on this side. So, this is marked as C2 and the radius is marked as R2. So, this is the geometry of the image formation by a lens. Okay, very simple, right? Now, the equation that we had got for the refraction at curved surfaces, we need to apply it for the surface ABC and surface ADC. So, let us check what do we get. You need to remember the equation that we have got. So, applying to surface 1, that is ABC, we get N1 as OB, N1 OB object distance, N2 BI1, that is the image distance, and N2 minus I1 BC2, BC1, that is the radius of curvature. Same way applying to the second surface, that is ADC, we get this as N2 upon DI1, DI1 that is because that is your object, N1 upon Di, that is because your image, N2 minus N1 upon DC2, DC2 that is because your radius of curvature. So, over here refractive index on the right hand side is N1 and also at Di1 is becomes the negative. Now, we have got the two equations. Proceeding further, now we can think of having a very thin lens. So, we can ignore the thickness. So, we can say that BI1 equals to DI1. Where is it? These distance. I am having an approximation that I am using a thin lens. So, this thickness I can ignore and I can say that BI1 is equal to DI1. So, if I have this approximation, let us add the previous two equations and you can see that I can cancel out few things, correct? Yes or no? And what remains is N1 OB and N1 DI. This can be taken as common and this is what is the ultimate final after adding both the equations. Same thing I have just put it up over here so that we do not have to go back. So, this is what we have got it. Now, let us assume that object is at the infinity. Always students keep in mind for a lens, if the object is at the infinity, your image is formed at the focus. So, you can say the image distance is nothing but a focal length. So, if OB is assumed to be at infinity, we know 1 upon infinity this term will go as 0, what remains is n1 di and the remaining equation. Now, let us divide both sides by n1, this will get cancelled out and what remains is this, because n2 upon n1 is written as n21, n1 upon n1 will get cancelled out and we get what is 1. Now, let us replace, as I have told you, if the object is at the infinity, image is formed at the focus. So, di is as focal length, BC1 is plus R1, DC2 is minus R2 using the sign convention. So, substitute this in this equation. So, once we have done that, this is what you get. That is, this is your famous lens maker's formula. It says 1 by f equals to n21 minus 1 into the bracket 1 R1 minus 1 upon R2. So, this is your lens maker's formula. Very important, students, you need to keep this in mind. Now, from few previous equations, I can have this equation equating the two sides. So, n1 upon OB, n1 upon di, this was object distance, image distance and the focal length. Again, I can use the sign convention. Okay, object distance is minus and the image distance is plus. So, over here we get the thin lens formula after substituting, and that is 1 by f equals to 1 by v minus 1 by u. So, very important equations is on this particular slide. You know the mirror equation that we had got was 1 upon f equals to 1 upon u plus 1 upon v. Over here slight change, we have 1 upon f equals to 1 upon v minus 1 by u. So, this is about the lens maker's formula. So, let us go ahead. So, let us move on to some images formed by a convex lens. What we will be doing now? We will be keeping the convex lens and we will be keeping the object at some different positions and checking out where the image will be formed. Okay? So, let us begin. First, I have already spoken about, I have the object at infinity. So, here I have got the lens and it is a transparent medium. So, I have got the two foci f1, 2 eyes of focal length, this is f2, 2 eyes of the focal length. Parallel rays coming from the infinity, object is placed at the infinity, you know your image is going to be a highly diminished one and it is going to be formed at the focus. So, this is when the object is at the infinity. Next, a different position. Now, the object has been kept beyond 2f. Okay. Now, here I have chosen two rays. The ray which is parallel to the principal axis goes through the focus. The second ray, a ray which goes through the optical center, goes undeviated, and wherever the two are meeting, I have got the image formation. And you can see clearly over here how is the image has been formed. It is a real image and an inverted image, and it is formed before 2f. So, if you are keeping it beyond 2f, the image is before 2f. Next, simple thing, object I have kept it now at 2f, I have used the same rays, the first one parallel going through the focus, second optical center goes undeviated. So, here is the image which is been formed, and this image is formed at 2f. So, keep in mind object is at 2f, image is formed at 2f and it is inverted real and of the same size. Now, let us get ahead, let us get the object in between f and 2f. Same two rays I have used, and what is the image? The image is highly enlarged and it is inverted and in real. So, if you are keeping it between f and 2f, image is beyond 2f. Now, I have kept the object at f. And have you seen these two rays, that is the refracted rays, are going to meet at the infinity. So, we say that when the object is kept at the focus, the image will be at the infinity. So, just keep this in mind, because next we will be learning about the optical instruments, we will be using this. Now, over here, I have brought the object more closer to the lens and it has been kept between optical center and the focus. So, same two rays parallel to the principal axis going through the focus, going through the optical center, goes undivided, and you can see these two rays are diverted from each other, they are not going to meet over here. So, we need to produce them backward, and here is where the image is formed, and this particular image is formed on the same side as the object, and it is going to be a virtual and it is highly magnified one. So, keep these two things in mind, students, that is because I will be using this when we will be learning about the optical instrument. Next, I have got the table telling you the same thing what we learned just now. Object at infinity, image at focus, it is really inverted and it is diminished. Beyond 2f, then image is going to be between 2f and f, it is going to be real and inverted, and definitely is going to be the diminished one. Object between 2f and f, then it is going to be beyond 2f, real and inverted and enlarged. If it is at f1, image is at infinity, real inverted and enlarged one. At 2f, I have told you image is formed at 2f, it is real and inverted and it is of the same size. Now, if it is between f and o, it is on the same side and virtual and erect and enlarged, which is over here. So, this is the image formation by a convex lens. Let us quickly go for the concave lens. So, I have a concave lens over here, object is being placed between f and 2f, same I am using over here. We know it is a divergent lens, so it is a parallel moving is getting diverted, and here it is passing through the optical center. So, these refracted rays are not meeting, we need to produce them backward. So, here is the image formation. So, this is the image formation by a concave lens. We use a concave lens, we will be getting a highly diminished images. If the object is very far away, the image formed will be more diminished. So, this is with regards to the image formation by the convex and by the concave lens. Now, linear magnification, just like how we learned for the mirrors, the linear magnification for the lens is given as h dash upon h, it is the height of the image to the height of the object, and it is given by v upon u. For the mirror it was minus v by u, for the lens it is v by u. So, you just have to keep in mind about the mirror and about the lens. So, this is the linear magnification for the lens. Now, few things, small things, how to get the power of a lens. How do we know the power of the lens? So, the simplest definition is if we take the tangent of the angle by which it converges or diverges a beam of light. So, simple figure I have got the ray diagram, optical center, principal axis. So, here is the ray coming parallel. What the convex lens does, it converges. So, it is going to move after refraction, is going to move here, right. In absence of lens, this ray would have moved it straight. So, what the lens has done, lens has converged the ray by how much? By this much of angle. So, this is the del. So, if this is the del, we know that this is also the angle del. So, let us take tan of del, we know it will be h upon f, f is the focal length. If h is 1, that is because we are talking about the unit height. So, what will remain is 1 by f. Now, let us go for the approximation of small angle del. So, what remains is del is 1 by f. Thus, the power is given as 1 upon the focal length. So, keep in mind power 1 upon the focal length. So, here I have got the SI unit dioptric given as capital D. So, 1 D is equal to 1 meter. So, the power is positive for the converging lens and it is negative for the diverging lens. So, this is how we get the power of lens. Now, students, some of you all must be using these spectacles. When the eye specialist prescribes a certain numbers about the power, you know what lens you have to use it. For example, if in case it is prescribed that a lens of power plus 2.5D has to be used, which means positive tells you it is going to be a convex lens of focal length plus 40. How is that? I know that power is 1 up by f. So, if your prescription says it is power minus 4D, then you know the one which you have to use is the concave lens of focal length minus 25 centimeters. So, students, you can just go back if in case you are using the specs or even if your parents are using, just go back and check out what is the lens being used. So, now let us move on to the combination of lenses. What does that mean? We have kept two lenses in contact, simple derivation and a short derivation. So, what it has, there are two lenses, thin lenses in contact. We have the object, the rays are moving here, after refraction you are getting the image as eye. Now, we know the thin lens formula, correct? So, we will have to use the thin lens formula over here. Now, this particular geometry I can show you like this. I have got the lens A and lens B. The lens A, we have the object forms an image I1 which is acting as an object for the second, and the final image that we have got is at I. So, let us go for the lens A. We apply the thin lens formula for the first one. So, we know that 1 upon V1, that is the image, minus 1 upon the U equals to 1 by F1. F1 is the focal length of the first lens. Same thing, apply the thin lens formula, apply it for the second lens. What do we get is 1 upon V, that is the image, minus 1 by V1, that is because that was the object for the second lens, equals to 1 by F2. Now, let us add equation 1, equation 2. What do we see? I can cancel out 1 minus V1 with 1 upon V1. So, what remains is 1 by V minus 1 by U equals to, adding the other side, it is 1 upon F1 plus 1 upon F2. Now, if the combination of the two lenses is just replaced by a single lens, then we can apply the lens formula to it and we will be getting the answer as this, 1 upon F equals to 1 upon V minus 1 by U. So, from this and the previous one, I can say that 1 by F equals to 1 by F1 plus 1 by F2. So, F is the focal length of the equivalent lens of the combination. So, what do we have understood this? If in case I have got two lenses in contact, I just need to add the reciprocal of the focal length to get the total, or 1 by F. What about in terms of the power? I know my power is 1 upon F. So, power of the combination is nothing but just the sum of individual powers. So, that will give me the total power. What about the magnification? Magnification is the multiplication of each magnification. So, have you all seen, once we have a different combination, I just can add up the powers to get the total, I just can multiply all the magnification to get the total magnification. Now, why do we do this? Why do we combine these lenses, or where do we use it? Now, this particular combinations are used in designing the lenses for the cameras, for the microscope, for the telescope. Okay, so, there where we make use of this lenses in contact. Okay, so that was about the lenses. Now let us move on to the prism. Again a very interesting topic. Okay, we will be learning about many new things. So let's begin. What we know is we can have the dispersion when the light travels through a prism, isn't it? We know this. When a white light is incident on a prism, it splits up into the 7 colors, the Vibgoid colors. That is termed as the dispersion of light. Isn't it some beautiful phenomenon? Okay, beautiful colors we have got over here, and that we already know it's termed as the dispersion, the splitting of white light into its constituent colors. Now, over here we have a small experiment just to tell you that the prism only splits the colors, it does not create the colors of its own. So, here I have got the first prism, and the second prism is just kept inverted. So, I have the white light coming, and we know there will be dispersion of light, and when the inverted prism is just kept in this form, all the 7 colors will emerge as the white light all over again. So, this experiment confirms that prism only splits up the colors which are already existing in the white light. Now, as we know that this splitting is as per the speed of each color, of each wavelength. There is some which deviates the most, some which deviates the least, okay, and it is as per the wavelength of the colors. Now, let us move on to another important derivation, that is refraction through a prism. Let me first show you all the ray diagram. So, simple ray diagram, no need to get scared of something really very simple, and you need to understand it. So, here I have got the prism A, B, C. There is an incident ray PQ incident at the interface A, B. Now, here is the interface separating the air and the glass, and back again I have the air. So, check out how is the path. So, my ray is incident at AB, there is a refraction. So, this is how it is going to move. At this point again it is going to suffer refraction, and this is the emergent ray, that is RS. So, this is actual path of the ray through the prism. Now, you can see the dotted lines. Now, these are the normals which are drawn, and why do we draw it? Because I want to get the angle of incidence and angle of refraction. So, here I have drawn the normal, I have got the angle of incidence I. So, the angle on this side it has been marked as R1, on the other side it is marked as R2. So, you can say this becomes the angle of incidence for the surface AC, and here is the angle of emergence. Now, a prism deviates the light, and how much is the angle of deviation? How do we get that? To do that, we need to just produce this incident ray forward. Now, in absence of prism, definitely the ray would have travelled like this, but what the prism has done? Prism has deviated the ray, and it is moving in this direction. So, this much angle is called as the angle of deviation. Okay, so this much the ray has been deviated by the prism. So, this is about the ray diagram, very simple ray diagram, and check out the arrows, students. Arrows are on the ray, not on the normal. So, please take care, arrows are to be shown on the ray of light. So, let us go ahead. Let us start off with the derivation. simple derivation. So, just pay attention. We have got over here the quadrilateral A, Q, N, R, that is A, Q, N, R. So, at the vertex, that is at Q and R, since this is 90 degrees, the sum of angle A and angle Q and R is going to be 180 degrees, correct? Angle A plus angle Q and R is 180 degrees. Now, take this particular triangle, that is Q and R, and we know that sum of all the angles is 180 degrees. So, it is R1, R2 plus Q and R equals to 180 degrees. Now, comparing the two equations, this equation and this equation, we can say that R1 plus R2 is A. Now, A is this angle, it is known as the angle of prism, this angle. Now, as I have spoken about the deviation, the total deviation del is the sum of deviation at the two faces. So, what does that mean? Here, this is the total deviation and this is equal to this angle plus this angle. So, how do I get this angle? It will be I minus R1, over here it will be E minus R2. So, doing that, I am getting this equation, and let us go ahead some simple steps over here. I am getting I and E together, and I know R1 plus R2 is A. So, it has been replaced by A. Now, if I plot a graph of angle of incidence, angle of deviation versus the angle of incidence, what do we get is this curve. As the angle of incidence increases, your angle of deviation first decreases, goes to the minimum, and then further it increases. So, we have gotten prism experiment where you will be checking this out. You will be increasing your angle of incidence, and you can check out that angle of deviation initially decreases, reaches the minimum point, and then it increases back. And this is called as the minimum deviation. And at this point, what you can see over here, it is I equals to E. At the minimum deviation point, angle of incidence is equal to angle of emergence, and this particular ray, that is a refracted ray, is parallel to the base, and because of that I can say R1 is equal to R2. So, as I have said, at the minimum deviation del m, I becomes equals to E, which implies R1 equals to R2. So, if these two are equal, I can say twice of R equals to A, or R equals to A by 2. In the same way, I can get del m as twice of I minus A. Why twice of I? That is because I have said I equals to E. So, if these two are equal, it will be I plus I, twice of I. So, twice of I minus A equals to I, A plus del m by 2. We just need to rearrange it, and there you have the refractive index of the prism formula, which is n/1 given as n2 n1 sine of I n upon sine of R, which is the Snell's law. Sine of I, in place of I have written this, and in place of R I have written A by 2. So, this is your refractive index for the prism, okay, from the Snell's law. A very important equation. Now, let us go for the small angle. Okay, let us have a small angle approximation. So, what do we get? We know from the previous slide, I have got this equation. If it is a small angle, sine of theta will be theta. So, what remains is this. I can cancel out the two, rearrange, and this is what I get for the thin prism. So, this was about the thin prism. So, we have learned about the refractive index for the prism and also for the thin prism. So, let us go for the very simple problem. So, the figure is given to you all. What it says, the angle of deviation suffered by the light ray shown in the following figure for the given condition. So, the refractive index of the prism is given as 3/2, and the prism is placed in the air, we know it is refractive index is 1. So, can you see here angle is 3 degrees. So, what can I say? It is a very thin prism, isn't it? So, use the formula for the thin prism, substitute whatever is the amount that you have got. 3 into 1 is 1.5, which is given as 3 by 2. So, angle of prism is 3 degrees, and this is what is the final answer that you get. Okay, a very simple problem on the prism. So, now let us go ahead. Okay students, so here was a small problem on prism. So, we will just stop over here. We will continue later in the next session. So, till then you just remember what we have done today. We have done some very important derivation, that is lens makers and the prism formula. Okay. So, just keep these two things in mind. Thank you students.
Prudent Scholars, powered by Lupin Pharmaceuticals.
अब आपकी सुरक्षा आपके हाथों में। ल्यूपी सेफ हैंड सैनिटाइजर, आपका और चेन्नई सुपर किंग्स का फर्स्ट लाइन ऑफ डिफेंस। अब आपकी सुरक्षा आपके हाथों में। ल्यूपी सेफ हैंड सैनिटाइजर, आपका और चेन्नई सुपर किंग्स का फर्स्ट लाइन ऑफ डिफेंस। अब आपकी सुरक्षा आपके हाथों में। ल्यूपी सेफ हैंड सैनिटाइजर, आपका और चेन्नई सुपर किंग्स का फर्स्ट लाइन ऑफ डिफेंस।